Testing, testing, 1, 2. All right. Um, all right, so we continue. All right, so I was referring to but1ene and why it was but1ene and but2ene, and telling you as to why it is but2ene. All right, so just to check, got logged out. Yes, yes, everyone got logged out, myself too. I don't know why. All right, so we'll see if we get logged out again. Just please log back in. Right. I don't know if it's my bad connection or something like that. I don't know what it is. But we're back again and we're going again. So we'll see how it goes. All right, so moving along. Next question. So it says, explain why these two hydrocarbons are isomers. Right? The reason why the hydrocarbons are isomers, they have the same molecular formula. Anytime you have hydrocarbons that are isomers, they are telling you that they have the same molecular formula. They have the same number of carbons, same number of hydrogens, same number of oxygens if oxygens are present, right? They have the same molecular formula. However, they may have a different structural formula or different arrangements. Right? They may have different structural formula or different arrangement. Right? That's why they are considered isomers. They have the same molecular formula, but different structural formula or arrangement. So part 4, are these two hydrocarbon members of the same homologous series? Give a reason for your answer. Right now, it depends on which ones you choose. When we go back here, right, if we choose but1 and but2ene, right, yes, they would belong to the same homologous series, which is alkenes. But if we had chosen the methyl cyclopropene, then that would not have been an alkene, that would have been an alkane. Right? So if you chose, depending on the ones that you chose, if you chose the but1ene or the but2ene, then yes, they would have both been alkenes, right? And therefore they would have had the same functional group, right? If not, if you chose the alkane and one alkene, then you would have had different functional groups. So one would have been saturated, meaning that it only have single bonds, while the other would have been unsaturated, meaning to say that there are double bonds present. All right, next question. The diagram shows the structure of a simple hydrocarbon and the products of two of its reactions. So you have dibromoethane, di because there are two bromines atoms attached to the compound, one on either side, hence dibromo. Bromo because it's representing bromine, et because there are two carbon atoms, and ane because there are only single bonds. So you have dibromoethane, and that is produced when bromine is added to ethane. Right? That should have been ethene. They have an error inside of the question. Right? That should have been ethene. So right here, this should have been ethene, ethene, because this here is an alkene. There's a double bond present. And when bromine is added to it, it becomes dibromoethane. And on the other side here, you have steam, and that produces ethanol. So when steam is added, steam is water, water vapor is added to this structure here, it gives you ethanol. So they ask you which structures are named correctly, and right here, this is our error. The ethane should have been named ethene, right? The ethanol, when we have two carbons, right? Anol, meaning that we have a OH group present. So this is ethanol. This group is named correctly. So number 3 is correct. Number 2 is wrong. And number 1 is correct. So our answer should be 1 and 3, which is B as in boy. So B should be the answer. All right. So next question. What are the names of the compounds shown in the reaction scheme below? So we have butane undergoing cracking to produce a compound W, and then that plus an alkene in the presence of steam gives us an alcohol, which in the presence of oxygen goes on to give us a compound Z, which is a carboxylic acid. How do I know that that's what it is? If we were to take, so this here is an alkene because there are only single bonds present. This is an alkene because of the presence of the double bond here. This here is an alcohol because of the presence of the OH group here. And this here is an acid because of the presence of the C double bond OH group right here. So they ask you what are the names of the compounds shown in the reaction scheme below? So W is ethane, W is ethane. So A or B could be correct. X is ethene, so A or B could be correct. Y is an alcohol, so it's ethanol, which leaves us with A. Y is an alcohol, which leaves us with A. And then Z is an acid, which is ethanoic acid. Et because there are two carbons, anoic acid because you have the C double bond OH group that is present. So your answer should be A as in apple. So let's check and see if we got those answers right. Yes, so the first answer was B as in boy, and the second one was A as in apple. So yes, that was correct. B was the first answer, and then A was the second answer. So that is correct. So let's move on. Next question. The diagram, question 3, the diagram shows the structure of a compound, and you can see the structure in front of you. And they ask you, which functional group does this molecule contain? They ask you, which functional group does the molecule contain? So you ask yourself, does it have a carboxylic acid group? Are you seeing C double bond O, OH? The answer to that is no. So we are not seeing a C double bond or OH group. So it's not a carboxylic acid. So which eliminates options C and D. That leaves us with A or B as our answer. The next thing, does it have an alkene present in it? How would we know if there's an alkene? We're looking for the presence of a double bond. Is there a double bond present? And the answer is yes, there is the presence of a double bond. So it considers the option B as our answer. So let's make sure, does it have an alcohol present? Is there an OH group present? And the answer is yes. To the end of the compound, there is an O bonded to H. So therefore, there's an alkene group present because of the presence of the double bond, as well as an OH group present because of the presence. There's an alcohol present because of the presence of that OH group. So the answer to this question should be B as in boy, which would make that one correct. Next question. Question 4. Increasing the number of atoms in one molecule of a hydrocarbon increases the amount of energy released when it burns. They ask you, what is the correct order to put them in? Increasing the amount of energy, increasing the number of atoms in one molecule of the hydrocarbon increases the amount of energy that is released. All right, so they ask us, what is the correct order from the least amount of energy to the most amount of energy? So meth is 1, et is 2. So from the least, we're looking for something that have methane as the first one, as the least amount of energy. So that leaves us with the answer as either C or D. Then we're looking to see which one have more hydrogens than the other. So ethene, E-T-H-E-N-E, will have less hydrogens because there's the presence of a double bond, which makes it an alkene. So it will go from methane to ethene, then to ethane. Ethane because the molecular formula for ethane is C2H6, while the molecular formula for ethene is C2H4. Right? So for the ethene, this is C2H4, while ethane is C2H6, and methane is CH4. All right. So the number of or the amount of hydrocarbons, the amount of carbons and hydrogens is increasing as you go from methane to ethene to ethane. Right. So the answer in the correct order should be from methane to ethene to ethene. Right. So the answer should be D as in dog. Question 5. The list gives the name of 4 organic compounds. And they ask you, which bonds do all 4 compounds contain? So you have ethane, ethanoic acid, ethanol, and ethene. So ethane, if we were to check that structure, so let's try to draw it out and see if we can figure out this one. Ethane would have carbon, met carbon. So we have hydrogen bonded all around. So you have hydrogens bonded all around this structure. Right? The ethanoic acid, you will have C bonded to C, double bond O, and then you have OH. And on this side here, we have hydrogens bonded to it. So if you're looking for a carbon-carbon bond, single bond, okay, let's see if the next one have that too. Ethanol will have C bonded to C bonded to OH. Right? Now, if you notice, they all are et, so it means to say that they all have 2 carbons. So hydrogens are bonded all around here. Right? So these, they all have a CH bond. They all have a C, the single bond C. So far they have the CH bond as well as the C single bond C, that's the first 3. They all don't have a double bond bonded to O. They all don't have a carbon-carbon double bond, and they all don't have a carbon-oxygen bond. But let's check the last one, ethene. Ethene have C double bond, C, and this is bonded to hydrogen here by hydrogen there. Sorry, my handwriting is terrible, guys. All right, so the bond that they all have in common is the carbon-hydrogen bond, which is this bond here, this carbon-hydrogen bond. They all have that bond in common. Carbon-hydrogen bond is common amongst them all. They all have that carbon-hydrogen bond, which makes C the answer. All right, I'm so messy, guys. Just now, let me clean it back up for you. All right, so to answer the question, the bond that they all have in common is the carbon-hydrogen bond as the bond that they all have in common. Somebody dirty up my board. Oh, I cleaned it. Yes. All right, so we're moving along. All right, so next question. Organic compounds may have names ending in ANE, ENE, OL, or oic acid. How many of these endings indicate the compound contain double bonds in their molecule? So ANE only have single bonds. All right, ANE only have single bonds, so this one is out. ENE have double bond present. OL represents an alcohol, this only have single bonds. And oic acid, this have C double bond O. So there's the presence of a double bond in this one as well, OH. Right? And this is C double bond C. So this has a double bond and this one has a double bond. So I have 1, 2. So my answer is B as in boy. All right. Now part B, sorry, question 7. Which structure is correctly named? So again, in order for us to check the name of the compound, we need to take it bit by bit and see which one is correctly named or which one is incorrectly named. So I'm going to take it one by one and check them out. So this says that this is ethanoic acid. Et means that there are 2 carbons present. So if we look at this, we have 1 carbon, 2 carbon, 3 carbons present, right? Which means to say that this should not be ethanoic acid, this should be propanoic acid. So A is not correct. When we look at ethene, this has 1 carbon here, 2 carbons here, but ENE means that there's the presence of a double bond. ENE means that there is the presence of a double bond. There is no double bond in here, so which makes this one incorrect. The third one, this says that this is ethanol. You have et, met, et, 1 carbon, 2 carbons. So therefore this is ethanol, OH. So therefore this is ethanol. So this one is correct. And this one is saying propane. So it has 1, 2, 3 carbons. So it is prop. Prop is correct, but there's a double bond present, which means to say that this is supposed to be an alkene and not an alkane. But they have ANE, so this part here is wrong. So that leaves us with C as our correct answer. All right, that leaves us with C as our correct answer. So the correct option is C as in cat for number 7. Okay, is that making sense so far, guys? Is that making sense? Anyone not following? All right. So let's go on. All right, so the next objective that we want to cover is objective 14.2, which is fuels. And which is fuels. And we want to look at a couple of things. Again, naming the fuels, name the fuels from which organic compounds could be obtained. What is the main constituent of natural gas? We want to be able to describe what petroleum is and also describe the properties of molecules within a fraction. And the last thing we want to do is name the uses of fractions. So let's get right into it. All right, so the first thing we want to find out, name the fuels from which organic compounds could be obtained. The first one is coal. We can obtain organic compounds from coal. We can also obtain it from natural gas as well as from petroleum, right? So the three main sources of fuel of organic compounds are coal, natural gas, and petroleum. The next thing we are trying to find out is what is the main constituent of natural gas? The main constituent of natural gas is methane. Methane is the main constituent of natural gas. Met being one carbon, ane means that it is an alkane. It has the molecular formula CH4, the structural formula of carbon bonded to 4 hydrogens, and it is displayed on the screen for you to see. All right, so the main constituent of natural gas is methane. Next, what is petroleum or what is crude oil, right? And your syllabus wants you to look at petroleum or crude oil as a mixture of hydrocarbons or compounds that are made up of carbon and hydrogen, right? So it is a mixture of a complex mixture of hydrocarbons and other chemicals. So for example, ethane is a hydrocarbon because it is made up of carbon and hydrogens. Butane is a hydrocarbon, it's made up of carbons and hydrogens. But there's something that you should note as the chains get longer. As we go from 1 carbon to 2 carbons to 4 carbons to 8 carbons, the longer the chain is, the less ability for it to flow, right? Meaning to say that the more solidified and liquidified it gets, right? Means to say that the less volatile it is and the more energy is required to convert it from a solid to a liquid gas. So the longer the hydrocarbon is, the more energy is required to convert it from a solid to a liquid to a gas. All right, so I'm gonna run a video for you guys. You let me know if you're hearing it, right?
By the end of this video, you should be able to describe how crude oil is formed. You should then be able to describe what's meant by a hydrocarbon and an alkane.
Okay, can you hear the video?
You should be able to use the structural formula for alkanes. I'm showing you here 4 different products. We've got plastics, petrol, pharmaceuticals, and cosmetics.
Okay, cool.
All of these are produced from crude oil, and that's what we're looking at in this video. We're going to start by looking at how crude oil is formed. Now, we find crude oil in rocks, and crude oil is a finite resource. That means that if we continue using it, crude oil will one day run out. Crude oil is formed over millions of years from the remains of tiny sea creatures called plankton, which were buried in mud. And I'm showing you a picture of plankton here. In this video, we're going to look at the molecules that we find in crude oil. Now, crude oil is a mixture of molecules called hydrocarbons. I'm showing you here one of the hydrocarbons in crude oil. This hydrocarbon is called methane, and it has a formula CH4. We can see that methane contains 1 carbon atom covalently bonded to 4 hydrogen atoms. The covalent bonds are shown by these lines between the atoms. As we said, methane is a hydrocarbon, and I'm showing you the definition of a hydrocarbon here. It's really important that you learn this definition. Hydrocarbons are molecules made up of hydrogen and carbon atoms only. This shows the molecule ethane, which is another hydrocarbon found in crude oil. Scientists call hydrocarbons like methane and ethane alkanes. We're going to take a closer look at alkanes now. This can look a bit tricky, but please stick with it and you will get it. Definition. Hydrocarbons are molecules made up of hydrogen and carbon atoms only. This shows the molecule ethane, which is another hydrocarbon found in crude oil. Scientists call hydrocarbons like methane and ethane alkanes. We're going to take a closer look at alkanes now. This can look a bit tricky, but please stick with it and you will get it. The key feature of alkanes is that they have the general formula CnH2n plus 2. What this means is that if we know the number of carbon atoms in the alkane, in other words n, then we can calculate the number of hydrogen atoms. And to do that, we multiply the number of carbon atoms by 2, and then we add 2. Going back to methane, we can see that methane has one carbon atom. So in this case, n equals 1. To work out the number of hydrogen atoms, we multiply 1 by 2 and then add 2. This means that methane contains 4 atoms of hydrogen. Looking at ethane, we can see that ethane has 2 carbon atoms. So in this case, n equals 2. To work out the number of hydrogen atoms, we multiply 2 by 2 and then we add 2. This means that ethane contains 6 atoms of hydrogen. Now, it's really important that you learn the general formula for alkanes. You could be asked to use it in your exam. Here's a sample question. Propane is an alkane with 3 carbon atoms. Draw the structure of propane. To answer this question, you'll need to use the general formula to work out the number of hydrogen atoms. Pause the video now and try this yourself. Okay, so propane has 3 carbon atoms, so n equals 3. To work out the number of hydrogen atoms, we need to multiply the number of carbon atoms by 2 and then add 2. Multiplying 3 by 2 gives us 6. Adding 2 now gives us 8 hydrogen atoms, and I'm showing you the structure of propane here. Try this question. Butane is an alkane with 4 carbon atoms. Draw the structure of butane. Again, pause the video and try this yourself. Okay, butane has 4 carbon atoms, so n equals 4. To calculate the number of hydrogen atoms, we multiply 4 by 2 and then add 2. This means that butane has 10 hydrogen atoms, and I'm showing you the structure of butane here. Now, scientists say that alkanes are saturated molecules. That's because the carbon atoms are fully bonded to hydrogen atoms. I should point out that you need to memorize the structures of methane, ethane, propane, and butane, as you could be asked them in your exam.
All right. So far, different hydrocarbons has different carbon chain lengths, and the longer the chain of carbons is, the higher the boiling point of that hydrocarbon. So it means to say, if I have something like methane, right, that would require less energy to be converted to a gas than if I had something like pentane. Pentane would require a lot more energy to convert to a gas because there are more hydrocarbons, there are more carbons present inside of that compound. Right? So different boiling points of different hydrocarbons is telling us one thing, that petroleum or fuel can be separated by fractional distillation. Right? And then the question you would ask me is, sir, what is fractional distillation? All right, let's not get ahead. Fractional distillation is the next thing that we're going to look at. Right? It is made up of a fractionating column that separates crude oil, right, or petroleum into different fractions, right? And that's because of this, we are able to get fuel oil that we could use in ships. We are able to get oils and waxes and polishes. We are able to get diesel to use for diesel engines. We are able to get kerosene, paraffin wax, naphtha, petrol, and your refinery gas and your cooking gas and so on. Right? It's because crude oil can be separated. And the reason why they could be separated is because they have different boiling points, right? If we go back, different hydrocarbons have different carbon chain lengths. So they are not the same length, all of them. Different hydrocarbons have different carbon chain lengths. So which means to say, the longer the chain of carbons, the more energy is needed to convert it from a liquid to a gas, right? So a large fractionating column with petroleum, how does it work? With petroleum is heated, right? As it heats, the different hydrocarbons begin to boil, and when they boil, they are converted from a liquid to a gas. So the first thing you have is crude oil entering. You place crude oil in at the base. Crude oil is in the form of bitumen, right? Bitumen can be collected and used if we want to put it on the roads to help pitch our roads. And that heat is applied about 350 to 450 degrees Celsius temperature of heat is applied to the fractionating column. And then as the carbons begin to boil, they begin to rise up, right? As they begin to rise, as you go further and further to the top, it gets cooler and cooler and cooler. And these hydrocarbons can then convert back from its gaseous form to its liquid form and be collected in different fractions. So I have a next video that I want you to take a look at.
So you should be able to describe how the hydrocarbons in crude oil can be separated by fractional distillation. You should then be able to state the functions of the important fractions. Over the last couple of videos, we've seen that crude oil is a mixture of molecules called hydrocarbons. Each hydrocarbon has a different boiling point. Longer chain hydrocarbons have a higher boiling point than shorter chains. Now, in order for the hydrocarbons in crude oil to be useful, we've got to separate them. And to do that, we use a technique called fractional distillation. In fractional distillation, crude oil is separated into fractions, and fractions contain hydrocarbons with a similar number of carbon atoms. Now, it's really important that you learn the stages of fractional distillation. This often comes up in an exam question. Fractional distillation takes place in very large columns, such as these ones, which we find in oil refineries. I'm showing you a drawing of this here. Firstly, the crude oil is heated to a very high temperature. This causes the crude oil to boil. In other words, all of the hydrocarbons evaporate and turn to a gas. The crude oil vapor is now fed into the fractional distillation column. The column's hotter at the bottom and cooler at the top. The hydrocarbon vapors now rise up the column. Hydrocarbons condense when they reach their boiling point. In other words, they turn back to a liquid, and the liquid fractions are then removed. The remaining hydrocarbons continue moving up the column. These now condense when they reach their boiling points. Now, there are a couple of further points that you need to learn. Very long chain hydrocarbons have got very high boiling points. These hydrocarbons are removed from the bottom of the column. Very short chain hydrocarbons have got very low boiling points, and these do not condense. They're removed from the top of the column as gases. Now, as we said, fractional distillation produces fractions. These contain hydrocarbons with a similar number of carbon atoms. Some fractions are used as fuels, and I'm showing you some examples here. Petrol and diesel are used to fuel cars. Kerosene is used as jet fuel. Heavy fuel oil is used to power ships, and liquefied petroleum gas is used in camping stoves. And we looked at how hydrocarbons are used as fuels in the last video. Now, some fractions are used as feedstock for the petrochemical industry. And the word feedstock means a chemical that's used to make other chemicals. And I'm showing you some of these here. So feedstock fractions are used to make solvents, lubricants, detergents, and polymers.
All right, so basically what he did just now was describe to you how hydrocarbons are separated in the fractionating column by the process of fractional distillation. And then he spoke of the functions of the important different parts of the fractionating column when it is separated, right? Looking at it again, you have at the bottom, you can have bitumen, right, which is used for roads and for roofs. Then you have fuel oil for ships and power stations. Then you have diesel for cars, lorries, and buses. Then you have kerosene for aircrafts. You have aircraft fuel. You have naphtha, which is used for making chemicals, gasoline or petrol, which is fuel for cars, and you have refinery gas or your cooking gas, which you use in your house. Right? So this is looking at the same thing in a different way, right? But all in all, fractional distillation is just telling us it's simply telling us that hydrocarbons can be separated by their different boiling points, right? It's simply telling us that hydrocarbons could be separated by their different boiling points on different fractions, right? So I'm gonna run another video for you guys. Hope you're still with me.
In our other videos, we have learned how fractional distillation is used to separate hydrocarbons into fractions with a similar boiling point. In this video, you will learn the names of some of the most important fractions and their uses. As you are now aware, large hydrocarbons have higher boiling points and so are removed at the bottom of the fractionated column. Smaller molecules condense higher up the column. We will now take a look at some of the common fractions as we move down from the top of the fractionated column. Some of the smallest molecules are between 1 and 4 carbons in length. This fraction has such a low boiling point that it is still a gas when it is removed from the very top of the fractionating column. This fraction is known as refinery gas or bottled gas. Bottled gas because it can be stored in bottles under high pressure. You could well have seen bottles of propane or butane running barbecues or heaters in your home, and these are examples of the refinery gas fraction. Petrol is between 5 to 7 carbons in length. It is still a fraction of small chain hydrocarbons, and therefore these vaporize at a low temperature and are easily ignited. This makes it useful as a fuel in the internal combustion engine of a car or other vehicles. Naphtha is not such a useful fuel, but it is a valuable source of organic molecules, which can be cracked to make more fuels or form alkenes. Alkenes can be turned into polymers, and polymers can make plastics, which are used in our everyday lives. Kerosene has an important use as a fuel for jet engines, in aircraft, and even in some rockets. Kerosene is also called paraffin in some parts of the world, and is a common fuel burnt in paraffin or kerosene lamps